0. And we're rolling, I hope. Here we go, class. We're up to lesson 5, and we're on limits, section 1.5 in your textbook. And fortunately, I'm not my brother Dave. I won't be singing the Eagles' Take It to the Limit one more time. First of all, we're only going to do this once, I hope. Only one take. Here we go. So we're on limits, of course. And here are some of the things we're going to look at. Talking about the limits graphically. In other words, we'll see a picture. And what are the numbers associated with the limits? Understand the definition of the limit. And a little bit of exotic stuff there. Some analytic techniques to evaluate the limits. What about one-sided limits? That sounds sort of scary, I guess. And unbounded behavior of limits. Oh, that's even more scary. You don't want functions that are unbounded. You don't know what's going to happen. In fact, that's sort of true. So here we go, class. Tighten your seatbelts. This is it. All right. So we're talking about limits. And we're going to look at a spring. And I have adjusted these slides in case you are looking at your own. This looks a little bit different. Yes, I changed it. Shoot me. No, don't do that. So here's a spring, and we just hung it up. No weights on it. Notice it says weight equals 0. And notice also that since there's no weight on it, it hasn't been stretched out. So we're going to look at two things. How much weight is on it and how much it stretches that spring. So we'll look at the bottom part here where we're going to hang the weights. How far down does that go because we hung a weight on there? Next. All right, here we go. We've hung a weight on there. So if you look at this part right here, the original spring, how far did this hook drop because we put the weight on the end? We've got distance from here to here if you're watching my cursor. Add some more weight. So originally we had no weight, then 3 whatever it was. It doesn't make any difference. You could think grams, pounds, kilograms, whatever you want to. Actually, you shouldn't say kilograms because that's not weight. Technicality. Taught physics for too long. 0 to 3 to 7.5, you can see it's stretching more and more each time. So on the second picture, it stretched from here. I guess you can't see, I just undid that. It's stretching from here down to there, not to there. When we put 7.5, whatever's on it, it's stretched from here all the way down to there. That's the stretch. Put a little bit more weight on it, 9.5 whatevers, and it stretched it from up here all the way down to there. Put some more weight on it. Now notice it says that every time you put some weight on it, it's going to have a stretch. Well, this says, consider a spring will break only when a weight of 10 pounds. So I guess it's pounds. Sorry, I missed that. 10 pounds. So we want to make sure we're real careful that weight doesn't go over 10 pounds. Notice we're getting awfully close. In fact, I would guess that most of you, if you lifted a 9.5 pound weight and then lifted a 9.999 pound weight, you might not be able to tell the difference. But the spring can. It's dropped just a little bit further. So the spring length approaches a value of L, limit. That's the stretch of it. And then it said that the limit of S, remember this represents the stretch, how much is stretched, how much has it stretched as W, the weight, approaches 10 pounds. That's L for limit. In this case, the L is 10. The mathematical limit notation looks like this. The limit of f of x, alias y, as x gets closer and closer to c, c is some number, 15 or 10 in this case. So we're sort of like a ninja, we're sneaking up on that 10, we're sneaking up on some value c. It's c because it represents some kind of constant. So we're sneaking up on it. Now, before we get to the end, there's two ways we could sneak up in that c. We could sneak it up from the left side. If we're sneaking up on 10, we might make it 9.5, 9.99, getting it from the lower end. But there's a second way you could do it. You could start at the top, not with a spring, but some other limits. So if 10 is the limit, you might say, let's try a 15, and then maybe a 13, maybe 11, and 10.5, and 10.01, getting closer and closer to 10 from the top side. So this says the limit of f of x, whatever that represents, as x creeps up on c from one side or the other is L. The limit of f of x as x approaches c is L. Here are three examples we're going to use. The first one has a function called x squared minus 1 on the numerator, x minus 1 in the denominator. We're going to find the limit as x approaches 1. Take a look at that. If we actually let it be 1, we'd be in big trouble, because the denominator would be 0. You talk to your calculator and ask it what it thinks of dividing by 0. Try it, and you'll see what it thinks of it. Error, not good. The second one, we've got the same problem. We can get close to 1, but we can't get to 1. On the third one, not quite the same, but we'll see how this works out when we see the picture of it. So we want the limit. We can't let it be 1, but we could get close. Because, for example, if we let x be 1.1, 1.1 minus 1 is 0.1, we're fine. The x squared minus 1 won't be 0. It doesn't even matter if it's 0 in the numerator. We can divide by 0.1 in anything. Same thing with the second one. The absolute value, we can figure out, it doesn't matter about that one. We can't let the denominator be 0. We can look at it and see what is happening. So here's the first one. They gave us a picture of it, and we can see what's happening. If we look at this part, the x squared minus 1 over x minus 1, if we get a whole bunch of points and connect them pretty much, this is what it looks like. Except for this little hole in the middle. Anytime we evaluate that fraction, it looks as though we get a 2. On the left side, you get a 2. On the right side, you get a 2. But as you look at that expression, you don't let it be 1. But as it gets close to 1, it gets closer to a y value of 2. From the right side, coming toward the left, it gets 3, 2.5, 2.1. It gets closer and closer to 2, but you can't actually put the 1 in. But you can see what happens. Either side is getting closer to that y value of 2. Keep in mind that when we talk about functions, the function value we're interested in is what is y. What happens when you're fiddling around with x? What happens to y? or fiddling around is letting x get closer and closer to 1. So we're a little bit sneaky. We're doing limits. We know that we can't let it be 1, but we can get really close. It's fun to get close. It's fun to see what it gets close to. In fact, it gets close to 2. The missing dot is represented by an open dot. When we use number lines, that's what we do. If we have a point that's included, we make a solid dot there, but since x minus 1 can't be 0 or x can't be 1, we have to leave it out. We don't dare let that be 1. Here's another way of looking at it. Usually we wouldn't have a graph to begin with. We'd just have our calculator, hopefully with us, and you can play around with it and see what happens. So here's what we're approaching. The top line represents x values that we could use. We're not going to use 1, but we're going to approach 1. Over here, we're approaching it from the left. Over here, we're sneaking up on it from the right. So what you do is you take these values of x, put them into your function, see what you get. If you put a 0.9 in this function, you get 1.9. If you put a 0.999, or excuse me, 2 nines, 0.99 in the function for x, you get 1.990. If you put 0.999 in, your function gives you 1.999. If you look at what is happening to the y values, you're getting closer and closer and closer. You're sneaking up on what? 2. If you tried it from the other side, start with 1.1. Put that in for x, see what the y is. The y is 2.1. If you put 1.01, that's closer to 1, you get something even closer to 2. Closer to 1, closer to 2. But you're not allowed to actually do it. But you can see what's happening to the y values. From the left, it's getting close to 2. From the right, it's getting close to 2. It's sort of like a game. What's it getting close to? You're not actually going to use 1, but you're going to see what happens when you get close to it. So think of it as a game. Here's the second one. Notice the function is up here, so you don't have to know what it showed about 3 or 4 slides before. Now this one's a weird one, because the top is the absolute value. If you didn't have the absolute value, you'd have x minus 1 over x minus 1. It gets a little bit complicated because the absolute value means you'll never have a negative answer. The bottom part is almost the same, except you will allow it to be negative. But in either case, you're not going to let it be a 1 because that makes the denominator 0 and everything blows up. So you put some numbers in, or you graph it on your calculator and see what's happening. In your calculator, we'll see that in a moment. If this number on top is already positive, and this is positive, you just get a 1. Because you have the same thing on the top and the bottom. That gives you a 1. On the other side, though, back here, when you have a number smaller than 1, this number on the bottom becomes a negative something, and on the top, you have the same number, but it's negative. And a negative something over a positive something over a negative something. The numbers are the same in magnitude, so they divide, give you 1, but the different signs mean you get a negative 1. So that's what we're looking at here. You might try it on your calculator just for the fun of it. Remember, we're not allowed to let 1 be that value, so you have wholes those two places. So, in that case, because two sides come to different conclusions, on the right side it looks like it's close to 1, on the left side it looks like it's close to -1. That's like having two people work on the same project, they come to different conclusions, so you come to the boss and say, we can't come to an answer. In this case, it means the limit doesn't exist because the right and the left don't agree. There's a little bit of quick calculator work. In fact, if you're real familiar with the calculator, you could actually set this up in a table function. Don't ask me offhand how to do that. I'm not real familiar with it, but I know it's easy to set up. You can just set up how the function works, and you can tell it what values to use for x, and it's going to calculate the y values. You can see what's going on. Notice on the left, we're approaching -1 from the left, because you're getting 0.9, 0.99, you're getting closer from the left. Over here, you're sneaking in from the right-hand side. Each of these values, it's closer and closer to 1, and the y value stays at 1. Over here, the y value stays at -1. They don't agree, so it doesn't have a limit. So imagine you're the boss, for example, and you have two workers for you. You take one part of the equation to one person, the second part to the other person. Say, okay, find out what the limit is on the left, find out what the limit is on the right. When they come in and don't have the same answer, you have to conclude there's no limit at all. Here's the third one. This one, notice up here on the left, I copied it over here. This one is what's called a piecewise function. Piecewise means this part on the right tells you which x's you're using. This right here says we're using any x that's not a 1. If it's not a 1, we're going to use the x. So if you use a 17, 17 is your answer. If you use a 3, 3 is your answer, and so on. This says if you're using a 1, your answer is 0. Now, I know this looks a little bit weird. What might help, see if I can get a pen here real quickly. Grab the pen. You might want to do something like this. Now, I'm sort of into a vertical x and y table like this. What I would suggest is that since you're talking about all the real numbers, with any kind of graphing, you might put 0 right in the middle. Something else might be appropriate in certain cases. This might be the number that x is approaching, for example. See what happens when x is 0, if it exists. You might put the positive values on the top. You might put some negative values on the bottom. For each one of those that you pick out for x, go up here to the function, how it's defined, and see what answer you get for y. So if I put a 5 here, just for one example, I'm going to pick an x of 5. Positive value, so I put it up here. You don't have to, it's just the way I do it. So if I take the 5, I go up here, I have to look and see what's going on with the x's. Okay? Well, 5 is not a 1, so I'm going to use this part of the definition. This says if x is not a 1, if 5 is not a 1, then you're going to use x. X in this case is 5, so I have my ordered pair of 5, 5. If I decide I'm going to use 3.1 for x, I go up here, I look again, Okay, what's going on? 3.1 is not a 1, so my y value is going to be 3.1. 3.1, 3.1. Down here on the negative ones, maybe we have negative 2 down here. How does that work? I'll go up here to the definition. Is negative 2 a 1? No. So I'll use x. X is negative 2. So negative 2, negative 2. After you do a few of those, you realize, hey, almost all the time the x and the y's are the same thing, except for if I do happen to pick that 0. When I pick a 0, I get 0. Oops. Yeah. If I pick, oops, I made a mistake. If I pick a 1, I get a 0. This is really messy. Put a real short one here, x, y. So if I pick x equals 1, or x equals 1, try to get these lines to stay away. When x is 1, the y is 0. And here's a picture over here. Almost all the time, when we pick an x, the y value is the same value. So this almost is the same as y equals x. Almost. But as they say, or at least they used to say, close only counts in horseshoes. So y equals x is the graph most of the time, but when you have an x of 1, which is right here, the y value is 0. So what you've got is y equals x most of the time, but right here, when you get x equals 1, you get a y value of 0. Whatever this function is, it's a little bit on the weird side, and it looks weird. The point is that it still has a limit. If you're sliding along this line from the left side, what's it getting close to when you get close to 1? What's sneaking up on 1? If you come along from the right side, it's getting closer to 1. At 1 itself, it drops down here. Give that some thought, come back to it a couple of times until you finally figure it out. Okay, so here's some pictures with x's and y's. You're probably familiar with it, but remember, f of x and y are the same thing. Put these x's in, it's easy to use this definition to figure out what the y value is. So we're going to get to the definition and some properties. And to be honest, some of these definitions aren't too difficult, really. And some of the properties are so simple. Honestly, it's so simple, you'll think, why did they even write it down? Yes. So, number 1, let me get a drink. So I'm going to sort of put this in my own words. You can put it in your own words later on. Where am I? There we go. Okay, so I'm talking about this first one. Saying that the limit of f of x approaches L as x approaches C means that f of x can be made arbitrarily close to the number L. In other words, here's the number L that represents the limit. Maybe it's a 17, 52, whatever y is getting close to. In other words, you could think of it this way. Y is getting close to some number. An example would be maybe y is getting close to an 85.7. That means that if you get x close enough to C, y is going to get extremely close to 85.7. That's what it means. If this is the limit, then you're going to get extremely close to L if you get extremely close to C using the x value. Second, if x approaches the same number from both sides, then the limit as x approaches C exists. Now if you look at this picture down the bottom, this is an example of the third one that we mentioned before. If you're sliding along that line, suppose you're traveling along that line in your Lamborghini or whatever, and you have a special meter on your car that shows you what you're getting closer to. You're getting closer and closer to that 1 value as your car gets closer to the 1. From this side, if you're coming on this side of the interstate, that meter in front of you, as you get closer to this point, the meter gets closer and closer to 1 again. So from the left, it's getting close to 1. From the right, it's getting close to 1. If they match, then you've got a limit. The strange thing is, we don't even care whether this actually works as a 1. It can be something strange. We could have a point up here, anywhere at all. All we care about is, what are we getting close to from this side? What are we getting close to from that side? If the two numbers match, we've got a limit, capital L. Third, if the value of y when x equals C, we don't care, in other words. Where am I? There we go. We do not care what our function does at C itself. When we actually, if we allow x to be C, we don't care what f of x is. We don't care what the y is. As long as the limit on the left side exists, the limit on the right side exists, and they match. We don't care what happens at that exact point. Odd, but limits are a little bit odd. So this is your chance to sort of get wild and crazy before we actually get to the differentiation part. So if you like being a little bit crazy, here's your chance. Limits are really weird. In fact, there's been controversy years ago about limits. Some places, some people didn't think they made any sense whatsoever. We were just sort of playing with things and not doing real math. We know now that it is real math. So this says, occasionally, remember this is y. What's y getting close to? Sometimes the limit as x approaches C is just f of C. That's when it's easy. If I can just throw C in for x, and put it into my expression. That's the simplest possible. That's what we're talking about right here. Remember, we're talking about what is this getting close to when x approaches c either from the top or from the bottom. Sometimes it's so easy that all you have to do is take this number, maybe it's 17, whatever your favorite number is. You can put it into the function and just use the function, find out what you get. What does C give you when you put C into your function? Sometimes it's as simple as that, direct substitution. In fact, here's a quick hint real fast. If that function f happens to be a nice polynomial, like x squared plus 7x minus 52, all you have to do is put that c value in for the x's, do a little bit of calculation, you've got your limit. Usually the case that causes the problem is that if there's an x in the denominator, that might cause the whole thing to blow up. If using a certain x value would make division by 0, that means that doesn't exist, you can't use it. But that doesn't mean there isn't a limit. It just means you can't use direct substitution. You have to play around with it a little bit. Experiment. See what the limit is. Some basic properties. Now, these might look a little bit like Greek. These are the ones that actually are very, very simple. So the first one, let's take a look over here. Number 1, what is this saying? This, remember, is our function. We're talking about the limit of some function as x is sneaking up on c. You're getting closer and closer to c. Well, if this number right here, the b, is just a regular number, for example, let's suppose we have the limit of 18 as x approaches, and let's say x is approaching 7. Now don't let this throw you. This is extremely simple. The limit of 18 as x approaches 7. Well, 18 is 18, really. X has nothing to do with what 18 is. 18 is 18. If this function right here is a constant function, it has no effect whatsoever on it. If you have the limit of pi as x approaches 92, what is it? Pi, because we don't care what x is. If it gets close to 92, it's still pi. If it gets close to 8,542, it's still pi. That's part number 1. Part number 2. Just about as simple. This says we've got a function that's described as x. So if we sneak something in here, our function is just x. Don't let that throw you. All we're talking about is y equals x. So here's an example. Now notice it says the limit of x as x approaches c is c. What are we talking about? The limit of x as x approaches, and I'm going to pick one of my favorite numbers, 42. What do I get? Okay, there's nothing fancy going on here. When I let x get close to 42, what is x going to be? Closer and closer to 42. If this is just x, then whatever we're getting close to is what we're getting close to. Not difficult at all. That's number 2. So if this is a constant, you don't change anything. If this is just x, it's very limited. If that's just x as your function evaluator. If you're getting close to c, you're getting close to c. Third, if you have the limit of x to the n, so this is just a little bit different from the one before it. The only difference is you've got an exponent. We'll call it n. So how about an example? Let's take the limit as x approaches, and let's say a 10. And we put an x here, and put anything we want to here. Let's put a 3 here for the n. You can put whatever number you want there. What's that equal to? Well, as x gets close to 10, x cubed will get close to what? 1,000. All you have to do is put the 10 in for the x. There's no denominators, there's nothing strange going on. You get to 1,000. It's that simple. So you just take this number, whatever you're approaching, take that and put it in x, and let your calculator do the rest of the work. And you've got your limit. That's number 3. Number 4. Number 4 is almost identical to number 3. So let's take a look at that. Now the limit of this something root, let me write that again. It's not being nice to me. Number 4, limit. And we're going to take a root, so here's our radicand. And we just have an x inside. We can pick anything we want for the index. So just to make it simple, let's suppose this is a 4th root. So we're taking the limit of the 4th root of x. Now we're going to say we're going to take that x and let it get closer and closer and closer to 81. What do we get? We can try playing with your calculator. Put numbers closer to 81. So maybe let your x be 79, or excuse me, 80.9. Let x be 80.99 and see what you get. And then try let x be 81.1. Let x be 81.01. See what you get for your expression. What do you get for y? In this case, you're going to get closer and closer to, you got it already? 3. Whether you come up from the bottom or come up from the top, come down from the top, all those values, the closer you get to x, the closer you get to 81, the closer this value gets to the 3. And that's going to work regardless of what your index is. The only catch is, notice, where am I? This expression right here says if you have an odd index, cube root, fifth root, seventh root, you're fine. If it's an even root, if it's a square root, fourth root, sixth root, eighth root, any one of those, then the number that's inside, which is getting closer to this number itself has to be positive. Usually that's not a problem, but it is a situation that you have to look out for. Now those are four relatively simple things, especially a couple of them. The others are just extensions on the limit of x. Here's some other ones that should make total sense to you, really. So let's take them quickly one by one, and with any luck, as I talk about them, you'll say, of course. Well, the first one might look a little bit more exotic to begin with. So let's throw in a quick example for this one. Limit as x approaches c, or a generic constant. I hate it when that happens. See if I can do it slower, and I guess not. It's going to be nasty. The limit as x approaches c of, now, back here, if you're following my cursor here, there's a b in here. B means it's some kind of constant. So up here we have the limit as x approaches c of, let's say, 17 f of x. What's that equal to? Well, one way of thinking of it is, if there's a constant in front of the function, you can slide that constant out in front and write this as 17 times the limit of the original function itself. So if there's a constant out front, slide it out front of the limit and just get the limit of f of x itself. That's what it means. So you take this b, that's just a regular number, even if it's a -5, slide it out front, and then take the limit of just the function itself. So this is that number being taken out front, and this has the limit of L, so you just multiply it times that constant that was in front of f of x. Next one, sum or difference. Just look at the sum part. The limit as x approaches c, f of x plus g of x. Well, this means that just split it up. Change this to the limit. I'm going to leave the x approaches c so I can actually get it done. We'll take this, split it up, and then g of x, add those two limits together, and that's what you got. All you have to do is add the individual limits together. If it's subtraction, subtract the two individual limits. That's all there is to it. Pretty simple. So that's number 2. Where am I? Come on, there we go. Number 2. Number 3, product. Well, if you caught on to this one, then this one should make a lot of sense. If you get the limit of a product of two functions, just split them up again. Limit of f of x times the limit of g of x. In other words, take the two limits and just multiply them together. That's all you have to do. So it's divide and conquer for number 2 and number 3 both. Number 4, almost exactly the same. The only difference here is that you're dividing instead of multiplying. If the limit of f of x is L, it goes on the top. The limit of g of x is k, it goes on the bottom. Real simple. The only thing you have to be concerned about is you have to make sure that bottom limit isn't a 0. Because when you throw that into your calculator, it's going to say, come on, Charlie, let's get with it. We don't divide by 0 here. Calculators are like that. Part 5. If you've gotten this far, you probably would do this almost by accident. This says we've got a function f of x, and it's being taken to some power. Pick whatever you want. You can even take a fractional exponent, or pi even as the exponent. Doesn't make any difference. Take the limit of f of x, figure that out, take it to the same power, so you work the L out first, take it to that power that's inside here, and get your answer. Again, divide and conquer. Last one. If you got number 5, you should have number 6. This one says, if you want the limit of this radical, just take the limit of what's inside, take it to the nth root, and get your answer. Again, like in the last slide, if n is even, you have to be a little bit careful. You just have to make sure that L turns out to be positive. If it's negative, you can't do it. Next. Okay, if you've got those down, we're on the home stretch even though we're only halfway through the slides. Find the limit of this. Here's where it gets really nice. Take a note of this. What you've got inside the limit for our function, remember up here we're talking about this function, we'll call it f. I know, not very exciting. This, notice, is just a polynomial. Now take this down. If your function is just a polynomial, you can take the number that's getting close to and just put that 2 in where the x's are, and you get it. So if you work on your calculator, store the 2 in your calculator as x, type in the x squared plus 2x minus 3, hit enter, you've got your answer. Quick. If you've got a polynomial, just put that number in for x. That's all there is to it. And what you're doing without thinking of it really is what you see here, because you're doing the 3 parts separately. This is like that f of x plus g of x. You got 3 simple functions. There's a function, there's a function, there's a function. All you have to do is find the limit for each one. 1, 2, 3. Add those limits together. Limit 1 plus limit 2 minus limit 3, and you get your final answer. Nice and simple. There's your individual limits. Either do it in your head or make your calculator do it for you. In your head's even better though, it's more satisfying. So here's what I said before. If the function is a polynomial and c is a real number, just put c in the x's in your polynomial and you'll get your limit. Next, some techniques. In other words, tricks. So the various tricks you can use, or techniques. Techniques make them sound more exotic. So if you've got a roommate or a friend, you might refer to it as a technique. It sounds like you're doing something much more complicated. So what this says is that you've got two functions. You've got f of x, g of x. They might not look exactly the same, but if the limit of g of x exists and you're approaching c, and also the limit of f of x exists as you're approaching c. If f of x equals g of x, then their limits are going to be the same. In other words, if f of x equals g of x, then their limits are going to be the same. And if it's a polynomial, just put that value c in for the x's and do the calculations. And you might notice this probably isn't something we need to know a whole lot, but P is C, that just means you put the C in where the x's are in the polynomial. It's equal to 0 only if x minus c is a factor. In other words, x minus c can divide into the polynomial evenly. Next, find the limit. So we're actually doing it now. Notice first of all, that's not a polynomial. Polynomials don't have denominators with x's in them. So we have to be a little bit more careful. We can't just throw the 1 in because it's a denominator 0. Not good. However, what we can do is we can factor the numerator. This numerator can be factored into two different factors, the x minus 1 and the x squared plus x plus 1. Once you factor the numerator, and this can be very handy, then you'll be able to divide x minus 1 into the numerator, you get 1, x minus 1 into that, you get 1, all that's left is the x squared plus x plus 1. Since that's a polynomial, then you can find the limit by just putting the 1 in where the x's are. You don't even have to worry about the fact that you're approaching 1. That doesn't matter because we don't care what the value is at 1, just the limits. And there's our limit. Just putting those 1's in where the x's were after we factored and reduced. Here's a picture of what we're talking about. The first graph, where am I? This is the graph of the function we were talking about. Notice the x minus 1 in the denominator and this more exotic numerator. After we factor, find the limit, we end up with the limit that's the same as the limit for this one. Almost everywhere, f of x and g of x are the same. The only place they're different is at x equals 1. We don't care because all we're looking for is the limit as x approaches 1. Next, in other words, note, if two graphs are identical except for 1 point, the limits will be the same. This technique or trick is called the dividing out technique or factoring, whatever you want to call it. Here's another one. Notice x is approaching 0. We can't just throw the 0 in. We'd have trouble. So what can we do? Okay. Can't substitute. It doesn't work. we can rewrite the fraction. Now this is a little bit exotic. You might want to analyze this later. By analyze, I mean take a look at the revised numerator up here. This part right here, if I'm real careful, and this part are very similar. Notice there's a minus in this one, but a plus in that one. So when we multiply these two together, the middle terms are going to cancel. This will give us a difference of squares, it's called. You actually might want to try this exactly one time, because this might be a technique you'd use sometime. What do you get when you split it up like that? Well, what we're doing is we're taking this part right here, we're changing the minus to a plus, we're putting it over here, and as you'll see in a moment, the numerator turns out to be something really nice. Before I go to the next slide, notice up here we've got a small problem. The problem is this. As x approaches 0, we can't use 0. Next slide. There we go. After we multiply, sneak back here for a second. See the two we're multiplying? The denominator turns into something that maybe doesn't look that great, but look what happens. I clean up the numerator because the plus 1 and minus 1 cancel each other out. I just end up with an x up there, which cancels out the x in the denominator. So what I've got now is I'm finding the limit of this as x approaches the same value that we were talking about earlier. Now in this one, it was a 0, as a matter of fact. Notice that by changing how that fraction looks, it's still got the same value, believe it or not, even though it looks totally different. By making that adjustment and making the fraction look different, I can actually put a 0 in where the x is. The 0 in here, that's no trouble. I can take the square root of 1, that's a 1, add 1, that's a 2. Put the 0 in, there we go. There's our limit. Just by a little bit of trickery or technique, it does have a limit. Remember, it didn't have to exist, but we can still find the limit. Remember, the old method is play with the calculator, see when it's getting close to it. With a little bit of technique, we can avoid that. Saves a load of time if we have some tricks at our disposal. One-sided limits. Now we've sort of snuck up on this one. What we're talking about is coming up just from the left side only. Ignore the other side. Just coming up from one side. Remember, you're a left-sided ninja. What is that function getting close to? If you're only on the left side, you get closer to that value of x. Or, what if you're a one-sided ninja on the right side and you sneak up on c from that side? What's the function equal? That's what the one-sided limits mean. You're either a left-sided ninja or a right-sided ninja. Limit, in other words. Now this is how we actually write it as mathematicians. This one right here, coming from the left, Now that's how we read most of our books, left to right. So if you're coming from the left, this is how we describe it. X approaches C, little minus sign up here. Now what does that mean? Okay, C represents some number. Maybe we're approaching 42, for example. What this means is that we're not going to let our X be 42, but we're going to take away just a tiny, tiny number. I'm going to call that number H. Let me try this again. So remember, H is a tiny, tiny positive number. So maybe what you'll get with this is X equals 42 minus 0.00001. Real close to 42, but not 42. If you take away a tiny positive number, that's what H represents, a tiny positive number. That's for this one. For this one, you're sneaking up on it from the other side. If you're approaching 42, you're approaching 42 from the right side, which means you're letting X be 42 plus a tiny, tiny positive number. So maybe 42.000001. Closer and closer and closer. That's what the positive means. It's toward the positive side of that number C. This means to the negative side of that number C. On the left, on the right. That's the notation mathematicians use and we're using. Now here's an example to play with. It says find the limit as x approaches 0 from the left, and then the limit as it approaches from the right. Here's what you get. So throw it in your calculator and play with it a little bit. So if I let x get close to 0, but just a little bit under 0. So maybe -0.0001. Real close to 0, but on the left. What do I get? When I look at this, if I'm finding the limit of that from the left, what do I get? I'll have -0.0002, and I'm taking the absolute value. On the bottom, I've just got x, which is -0.0001. The top, we're going to take the opposite of that one, 0.0002. On the bottom, we've got the x, which was 0.001. Looking at those, positive divided by negative, negative, and this gives you a 2. That's from the left. -2. We were talking about this part of it getting closer and closer to 0 x's. What is the y value? Well, the y value is 2 all the way up to the number we're approaching. On the other side, the number on the top and the number on the bottom will both be positive. Absolute value doesn't change anything. So what you'd have is you have a positive here, you have a positive here, this would be positive, and that would be positive, and that's what you see right there. If you don't quite get it, try the numbers. Make a chart for yourself. X and Y values, and do the ones on the left side. Negative numbers here because you're on the left side, and see what you get for Y. And then do the same thing on the right. X values, Y values. In this case, since you're working from the right, these will all be positive values. We'll calculate what the Y value is that matches up from our function. You'll see what happens. And this graph over here is what you'll get when you take those points and put them together on some graph paper. Remember, I think I mentioned this in one of the classes at least. If you go to mathbits.com, it skipped a little here. If you go to that website, go about halfway down or so, on the right side, you'll see something that has to do with graph paper. You can just click on PDFs. You can pick which kind of graph paper you want to use, print it out, almost totally free. You don't have to go to the bookstore. You don't have to go to an office supply store. Almost free. Next. So from the left, f of x equals 2, because from the left, and from the right, you get a positive 2. Notice that those aren't the same. We've got two one-sided limits. They both exist, but they don't match. So this, I think it's the last property, don't hold me to that. Existence of a limit, and we'll sort of emphasize that. The left and the right have to match for you to have a limit. Left side limit, right side limit. If they exist and they're the same, you got a limit in capital letters. Here's one example. This one is a little bit crazy, but it is something that you could use. We've got another piecewise function, and it looks something like this. The limit of x as x approaches 2 from the left. So x approaches 2 from the left. So where is 2? 2 is here, excuse me, and we're coming up on the 2 in this direction. What's it getting close to? It's getting close to 4. From the right, what happens? Well, from the right, we are coming in from the 3 toward the 2, so we're sneaking up on this part of the graph. What's it getting close to? It's getting close to this, which is the 6. The limit exists on the left, the limit exists on the right, but they're not the same. So you've got a left side limit, you've got a right side limit, two one side limits, but they don't match. 4 and 6 are not the same. And last of all, what about when things don't get close to one particular number? So this is what we're talking about. Let me get a drink here a sec. So we've got a fraction here. 3 over x minus 2. And x can be various things. It can't be a 2. That's off limits. But we can let it be 1.999. or we can let it be 2.0001. What's happening? Well, play with it again. Maybe make your own table. If you know how to do it in the calculator, fantastic. I'm not against that. Try numbers from the left. Make another table. Try numbers on the right side of 2. See what happens. If you graph it, oh my gosh, what's going on? If you come from the left, now imagine you're on the function interstate. So you're back here. Remember, as you read, you go from left to right, so let's slide along the interstate here. What happens when you get close to the x value of 2? Well, as you get close to 2, the y values get negative but really, really big. On the other side, what happens? Well, as we're coming this direction on the interstate, the function interstate, all of a sudden when I get real close to 2, the y values get huge. Translated, that means f of x is going to get approach negative infinity if you approach x from the negative side or from the left side. On the right side, as you approach 2, f of x approaches positive infinity. A little bit of playing around and you can find out what that is. This is how we write it symbolically. Notice that the 2 don't match, so you don't have a limit. As a matter of fact, even if they did both approach positive infinity, the limit still wouldn't exist because infinity is not a number. It's like getting on some interstate that goes north-south and you head south. When do you get to south? You don't get to south, you just head south. There is no limit. If you get on one of the interstates that goes north-south and you head south, you never get there. That's what this means. A limit of positive infinity means it doesn't exist. Whether these 2 match up doesn't make the limit exist at all. And that is it. So let's see. Let's get rid of those. And that's it for this time. I hope you followed what I'm going through, and I hope you go back and review a little bit of it and have some success with the actual exercises. If you have any questions, just check with me and I'll try to lead you in the right direction. Until next time, take care and keep smiling. Bye-bye.